Hello everyone, I'm Abhijit Singh Rana and I will be presenting our paper titled Blended Physical Digital Kinesthetic Feedback for Mixed Reality Based Conceptual Design in Context. Prototyping is a valuable tool in promoting creative idea generation in early design. The efficacy of low fidelity prototyping goes as far back as work by Rod et al., who noted that the key advantage of low fidelity prototyping is in supporting the refinements in product requirements and preliminary analysis in the early stages of design. Lim et al. Noted that prototypes can be tools to explore the design space in that they are purposefully reformed manifestations of design ideas. Gerber notes that low fidelity prototyping affords design practitioners the opportunity to learn from failures, thereby providing them confidence in their creative ability. We find three broad categories of prior work in HCI and computer graphics based on virtual prototyping. In first category, users utilize a CAD-based WIMP software to generate digital prototypes, which are then manufactured using rapid prototyping techniques. The second category uses spatial user interfaces and mid-air interactions in mixed or virtual reality. They either use gestures or handheld controllers, but there is no tangibility integrated into the virtual environment. Then we have a third type, which is tablet-based, where we see some tangibility because of the tablet, but the interactions are not spatial and are limited to a 2D space because of the tablet. So there's a knowledge gap in terms of how to bring in tangibility of physical objects into 3D virtual spaces. Even though we have works that overlay digital information in visual realm over physical space, we don't see much work where tangible interfaces can be integrated with the mixed and augmented reality. Context plays an important role in the design process during early phase design ideation. As a concrete example, we decided to consider wireframe modeling as a prototyping scenario. Prior works have used wireframe modeling to create digital and physical prototypes, as it provides an easy way to generate quick prototypes during the design ideation phase. In this work, we defined the notion of blending physical-digital kinesthetic feedback. We use a physical object, say a 3D printed human head, that provides a specific design context for a user to generate ideas through physical manipulation of and on the object, say drawing a digital sketch of a helmet in the virtual environment. The user also experiences a digital kinesthetic feedback while drawing the digital wireframes. The fundamental challenge we faced is that achieving precise spatial manipulation in conventional virtual environments is difficult due to interactions at the arm's length. This is critical, especially for prototyping tasks, where the user must focus on the creative task rather than being distracted by the lack of spatial control. To address these challenges, our approach in this work was to create a tangible interaction workflow that integrates physical and digital spaces together in order to provide spatial control to the user during prototyping tasks. For this, we present a case where such control can be obtained through direct interaction with the physical objects in closed-range spaces, known as the peripersonal space. To enable a smooth integration between the physical and digital spaces, we developed the idea of blended haptic feedback, wherein not only the user able to touch the physical object, but simultaneously feel the kinesthetic feedback from object in the virtual environment. Main factors were considered while designing the workflow. The location of the action space with respect to the body is a key factor while designing the interface. We utilize the action field theory to determine the motor control afforded by the system based on the proximity of the physical object to the user. We define the interaction such that the actions performed by the user are close to the body. Galligani et al. Made a note that active tool usage in the user's peripersonal space enhanced their proxemic perception, allowing for precise control of actions. The system provided three types of feedback: visual feedback through rendering of the drawn curve, tangible feedback from physically touching the object with the stylus tip, and kinesthetic feedback by the haptic device based on the curve geometry. The goal of this setup was to enable users to do quick design ideation through virtual prototyping. We choose curved networks to model the prototypes because it offers a good representation for quick prototyping, and similar to sketches in 2D, 3D curved networks still have the ability to express the overall shape without the necessity of complex 3D modeling. There are two main issues that need to be addressed in the geometric modeling of curved networks. First, the initialization of a single curve on the surface of the physical object, and second is the refinement of a curve to ensure the curve to be constrained on the surface. Our first aim is to determine the corresponding tangent vectors m0 and m1 in order to generate a cubic Hermite spline. We achieve this by using the mesh model in conjugation with the points probed by the user. It is obviously not true that a spline defined using our method will always remain on or above the mesh. This may especially be more likely when the endpoints of the cubic Hermite are defined on a high curvature region or are farther apart on the mesh. To resolve this problem, we define the spline by applying an iterative curve splitting approach until the entire curve is outside the mesh. There are four different types of virtual haptic feedbacks that the user is getting from the system. First is a spring force, second is a wire bending force, third and fourth are a type of magnetic snapping force to assist the user to locate the digital curve and control points respectively. On to the experiment design and findings. The goal of the experiment was to investigate the role of blended haptics in supporting design ideation. Here we answer three main questions. Which type of haptic feedback reduced the barrier of entry to tool usage and why? Secondly, which haptic feedback offers the potential for improved design ideation? And thirdly, does a reduced barrier of entry correlate with improvement in design ideation? If so, why and how? Into two groups, namely physical and virtual. We recruited 38 participants, 19 per group, enrolled in undergraduate and graduate programs in the university. Most participants didn't have any experience of sketching in virtual interfaces or using a haptic device. We designed two sets of tasks for each setup to measure the quantitative and qualitative aspect of the workflow. In the quantitative experiment, participants were asked to locate and pick points on a cube using the haptic stylus. In the qualitative experiment, participants generated curve networks on digital and physical models. The physical group was provided with a 3D printed counterpart of a digital model that was being shown on the screen, while the virtual group relied solely on the haptic feedback received from the haptic device to get a feel of the model. Here are some of the models generated by the users of both physical and virtual groups during the study. We computed the kinetic energy by accounting for the movement of stylus and the turntable throughout the curve network design process. This gave us a quantitative metric to measure which haptic feedback reduces barrier to entry in tool usage. To quantitatively measure which method potentially improves the design ideation process, we conducted an iterative study. The raters were asked to rate each curve network based on well-established novelty and variety metrics. Two expert raters evaluated the curve networks generated by the users. We also asked the raters to rank each design based on the number of factors that a design might have considered to give a quality score. We found out that users spend more energy using their dominant hand. When we compared the energy spent between the two interfaces for dominant and non-dominant hand, we found a significant difference in case of the dominant hand. Note that here we considered the weight of 3D printed models of the turntable. Just for sanity check, we removed the weight from the calculations and when objects' weight are considered and when objects' weight are not considered. Moving on to the ideation metrics, the physical interface afforded the users to create more novel designs. Variety ratings were similar for both the interfaces. We also saw an increase in quality rating for the virtual design. This is interesting since it shows that the virtual interface helped users make design of a higher quality. In conclusion, we concluded that providing different type of haptic feedback changes the design outcome by encouraging different processes and due to different user behavior. There is a fine balance between user performance and user experience, and who do we value more, and how real is real enough.